All right, in this video, we're going to take a look at the history of the atom. So first off is going to be a quick flowchart of going over the different people that we are going to talk about. So the first one we're going to start off with is going to be Democritus. He came around in about 460 BCE. So this does go back thousands of years, the idea of the atom. Now in 1803 came along a person named Dalton, and he came up with different ideas that he thought all atoms had to follow. About 100 years later, a little less than that, in 1896 came a person named J.J. Thomson. 1909 came Rutherford. 1924 was Schrodinger. 1927 was Heisenberg. And now we have the modern atomic theory. Now, starting with Democritus, he was a Greek philosopher who came up with the idea of the atom using a thought experiment. Now, because this was ancient Greek time, they did not have a lot of technology. They only had what they could think of. And so he came up with a thought experiment of if you had a sphere of any type of object and you cut it in half, that you would get two smaller spheres. And he thought that if you continued this path, that there has to be a certain point at which case you can no longer cut it in half. So he thought that if you kept on cutting something in half, eventually there is going to be a stopping point. And he was correct that there is going to be a point at which case matter gets so small, if we were to cut it in half, it no longer is matter. It's no longer something that we can really recognize. And so what he termed was the word atomos, which became the Greek word for atom, which is what we use today. All right, Dalton's atomic theory. So this and everything was a few hundred years later. He came up with different postulates that he thought that all atoms had to follow no matter what. Now, our first one is that elements are composed of tiny particles called atoms. He got that first one from Democritus. Our second is that all atoms of a given element are exactly identical. So he assumed that all hydrogen atoms looked exactly the same. He assumed that all carbon atoms looked exactly the same. So he just assumed that any type of element, all of those atoms are essentially copies of each other. The third one is that atoms of one element are different from atoms of all other elements. So this does make sense that hydrogen is going to be different than helium, or hydrogen is different than carbon. So our elements are going to be different from all other elements. And that's going to be what makes them unique. Our fourth postulate is that different atoms form compounds in whole number ratios. So what that means is that our elements, our atoms, are going to form whole number compounds. And those are going to be in different types of ratios. But the big thing is that we're going to have one atom and it's able to form a compound with two other atoms. We're never going to have a 1.5 atom or a 1.75 atom. It's going to be a whole number of our atoms that are going to form these compounds. And then the fifth postulate that he came up with was that chemical reactions only involve the rearrangement of atoms. And so the fifth postulate really gets into the idea of the law of conservation of mass. So what we start with is going to be what we end with. And that chemical reactions are just rearranging the atoms to form something new at the end. But we're still having the same mass and the same starting and ending material, just in a different form. After Dalton came J.J. Thomson, and he discovered that atoms have negative particles called electrons, and he did this through something called the cathode ray tube. Now, his model of the atom became known as the plum pudding model. And so what he assumed with these electrons were that the electrons were spread out randomly throughout essentially a sphere. And so he just kind of assumed that these electrons were floating around, just kind of around a central point, not really doing much, and their location was random. And this and everything led to the idea of plum pudding, which is a British dessert, which he and everything obviously thought of. After him came Rutherford. He discovered that atoms have a dense positive center by performing what is known as the gold foil experiment. And now, what he learned from this was that the atom is mostly empty space. So, the big thing that he really learned was that atoms have a nucleus to them that have the protons. So he discovered and everything that the nucleus of an atom has protons in it and that it is extremely dense. Now, what the gold foil experiment is that he essentially shot radiation at a really thin piece of gold foil, and he noticed that a lot of the radiation was able to pass through the atoms in that gold foil. But every so often, a little bit of the radiation was bounced back or bounced in a different direction, which only could have happened if there was a really dense positive nucleus in the atom. And then anything else that went through led him to the idea that the atom is mostly empty space. Probably the most famous person on this list is going to be Niels Bohr, and what he discovered that electrons orbit the nucleus. So this is going to be the most common model that we see, and it became known as the planetary model. So he really assumed and everything that the atom has a nucleus and the electrons are going to orbit around that nucleus at a given speed and distance. He labeled and everything the different energy levels as like orbits, and the electrons would follow those orbits in a very predictable manner. Now, he later found the neutron with the help of James Chadwick, and they found the neutron through mathematical calculations. Now, kind of bringing into our modern atomic theory, certain revisions have been made to Dalton's atomic theory once we really learned more about the atom. And so we essentially kind of simplified Dalton's atomic theory a little bit, and we had to get rid of a few things. So, our first is that all matter is made up of atoms. Atoms themselves are composed of protons, neutrons, and electrons, and that each element has its own atomic number, which is equal to the number of protons in its nucleus. So, the atomic number and the number of protons is going to be the same. So the really big part of this is that the number of protons is essentially the identity of that element. So if we change the number of protons, we're going to change the element. Now, this leads in everything to the idea with Heisenberg. So he really took the idea of the atomic theory and really expanded on it and made it much more complicated. So scientists such as like Rutherford and Bohr have been working on the atomic models. Now, one scientist's discovery led to profound implications for existing models, and that and everything was Heisenberg. So he was a German physicist focused on the interactions between photons, which is going to be light, and electrons. So he and everything didn't really go out looking for the idea of really redoing the model of the atom. He really just kind of stumbled upon it. So he was looking at these interactions between photons and electrons, and what he noticed is that whenever photons and electrons interacted, the position and velocity of the electron changed. So essentially, by shining a light on these electrons, the position and velocity of those electrons ended up changing. Now, why and everything that's really important is because it led to the idea of this Heisenberg uncertainty principle, which states that it is fundamentally impossible to know precisely both the velocity and position of a particle at the same time. Now, What this really means, kind of putting this into a perspective for a school, so let's say in everything that you were walking through a hallway and you were being watched. So just in everything, the act of watching you, we wouldn't know exactly how fast you were going or what position you were in. And so this really leads to kind of a weird state that electrons are able to be in. Now, this means in everything that it's impossible to assign fixed paths for electrons, like the circular orbits in the Bohr model. And so this really complicates the model of the atom because what we have to use are going to be areas of probability to describe where an electron is most likely to be found. Now, what an area probability is going to be like if you leave the classroom and you are going to go somewhere, we have a rough idea of where you're going to be, but we don't know exactly the exact location. So, for example, if you leave the classroom and you go to the library is an area probability of where you are, but I don't know exactly where you are exactly in the library. Maybe you're in like the fiction section, maybe you're in the nonfiction, maybe you're reading poetry. So, all I know is that you're probably in the library. I just don't know exactly where. And electrons are the exact same way. We have these areas of probability of where they are most likely to be found, but we don't know that for certain.